Good morning everyone. Today we will study about the first application of Gauss law, that is electric field due to a uniformly charged infinitely long straight wire. For that, let's consider a part of this infinitely long wire which is positively charged, and we are using Gauss law here. So again we have to consider an imaginary, that is hypothetical Gaussian surface around this wire such that the electric field is same at any point on it. So let's consider this is our cylindrical Gaussian surface such that the wire is at the axis of the Gaussian surface. So now in this case, this is the wire which I am showing by this, and this is the cylindrical Gaussian surface around it where wire is at the axis, and if we consider this as at the axis, so this is our cylindrical Gaussian surface, right? How many surface areas this cylinder has? It has 3 surface areas. For example, this is the lid, this is the base, and this is the curved surface area. Let's mark these surface areas by, this one is suppose first surface area, this is the second surface area, and this is the third surface area. We know that electric field due to this wire will be normally outwards. So let's mark the electric field here. We know that since the wire is at the axis of this cylindrical Gaussian surface throughout, so electric field due to this wire will be normally outward. So here it will be this way, surface lid this will be this way, base this will be this way, and here this will be this way. So if we mark this, comparing this, the electric field on this surface will be in this direction. Electric field due to the curved surface will be in this direction. And electric field on this side will again be normally outward. So you can say that the electric field here is normally outward. And here also it will be normally this way and this way. On both the sides it will be away from the wire. So this is the direction of electric fields over here. So by Gauss law, we all know that what is the total flux by Gauss theorem? By Gauss theorem, the total flux is equal to charge enclosed upon epsilon naught. Now here we have considered a Gaussian surface. We can use another formula for flux, that is E dot ds. And for every surface of the Gaussian surface, we have to find out the total flux. So total flux will be flux due to the first surface plus flux due to the second surface and the flux due to the third surface, which one is curved surface, right? We know the formula for electric flux, and electric flux is E dot ds1 and then integrate for the total flux due to this surface. So what is ds1? We have considered a small surface area ds1 over here whose direction is normally outward. We know that the direction of the surface area vector is always normally outward. That means if we have this surface area, the surface area vector will be this way for this top surface. So we can say that here the theta is 90 degree between ds1 vector and E vector. So this is small surface area ds1 taken by us, and the ds1 vector is this way and this is this way. So E dot ds1 will mark there in next step. Second surface is this, that means the base. So its area vector will be normally outward to this surface. So look at this surface. This will be the area vector. So you can say that if ds2 is the small surface area taken on the base, then this vector will give the direction of ds2 vector. And we know that the electric field is outward from the wire. So the angle between ds2 and electric field vector will be 90 degree. Let's consider a small surface area here now on the curved surface. Let's consider this as ds3. Now at every point on the curved surface, the area vector will be outwards. So at this point, the area vector will be this way. So you can say that ds3 vector is this way. So here the angle between ds3 and electric field is 0 degree. Now let's use the formula here. E dot ds1, if we integrate it, we get the total flux due to the first phase. And if we integrate E dot ds2, we will get the total flux due to the base. And if we integrate E dot ds3, we will get the total flux due to this curved surface. Now let's put the angles and solve it. What the answer is, let's check. This is E ds1 cos of, look at this, 90 degrees. Let's integrate, plus E ds2 cos of, look at this, 90 degree, plus integration of E ds3 cos of, look at this angle between ds3 and E vector is 0 degrees. So this makes it this one. Now this on solving becomes cos 90 is 0. So there will be no contribution to flux due to this lid. This cos 90 is also 0. So lower part of the cylinder also does not contribute to any flux. Plus E is uniform, so can be taken outside the integral sign, ds3, and cos 0 is 1. So if we simply integrate ds3 means on curved surface area, we have small surface area ds3, and if I want to know the total curved surface area, ds3 integration means the total curved surface area. What is the formula for the total curved surface area of a cylinder? We know that curved surface area of a cylinder is 2 pi RH. Curved surface area of a cylinder is equal to 2 pi RH, where H is the height of the cylinder. In this case, we have taken that L is the length of this cylinder. So we can say that ds3 integral means the total curved surface area of this cylinder. So what will be the formula? That will be 2 pi R L. So this gives us total flux. So this is pi total. Let's consider this as equation 1 and this as equation 2. So from equation 1 and 2, we can write that E into 2 pi RL is equal to Q upon epsilon naught. So if we solve it, we get E is equal to Q upon 2 pi RL epsilon naught. So if we look at this part, what is this? This is lambda, which is charge per unit length. So we can replace this by lambda and our equation becomes E is equal to lambda upon 2 pi epsilon naught R. This makes it that E is inversely proportional to the distance of the point from the infinitely long straight wire. If I want to draw the graph between the electric field and distance R from the wire, since it is inversely proportional to the distance, so the graph will be like this. That's all for now.